facts really don't care about your feelings. It's actually quite the truth, my friends. So what we are going to do is we have a question, and I'm going to find this question. Hey Boris, welcome back. And the question is as follows: a hydrogen atom starts out in the following linear combination of stationary states. Okay, so basically there are two stationary states. Excuse me, bored. Hey, you must be really bored. There are two stationary states, and if you guys remember the quantum wave, right, when you take a snapshot in time, the snapshot is in 3 dimensions. And I'll show you which ones we have. I don't know if they've included both in the diagram, but there is 211, that's one of them. So if you look here, that there is 211 squared, okay, and that's the 3 numbers. So that 2 means energy level 2. 1 is the type of orbit on the radius, and M is called the magnetic quantum number, and that is, I don't remember, I think it's to do with the spin of the number. I always forget the technical terms. I'm better with the maths, obviously. So that is the 3-dimensional wave. There's another one. There's also 2 1 minus 1. So that's 2 1 1 and 2 1 minus 1, and together that's how the atom starts. Okay, and what we want to do is figure out where it's going to go, right? And what the atomic nucleus is, the radius is going to be of the electron orbiting the nucleus. And the funny thing is that it gets way too complicated when you move up in atoms, in types of atoms. So if you start with hydrogen, it can be calculated mathematically. Even on paper, it takes like 5 pages to work out. It took me an hour, and then the computer takes like 3 seconds. So I guess to show you that we're going to get taken over by computers, my friends. All right. So the representation, Captain Deltron, representation is this. Here it is. That's the 3D wave, right? So what we can see here, if I can try and zoom in, that right there is the 3D wave, because t equals 0. So otherwise it would be a 4-dimensional wave, but here t is 0. So it's a snapshot at the point in time that we're calling 0, right? And r is 3D, right? And it is made up of 2 waves, 2 3-dimensional waves. So it's 1 over root 2 of these 2 3-dimensional waves. Okay. And so the question is, construct the 4D version of the wave. And that's actually not that difficult to do, because what we have to do, if I can find my working, is right here. This is something I've prepared earlier. All you have to do is get the first wave, multiply it by the time wave, and it's the energy level 2, because you can see the first one here, that's n. That the first number is n, which is the primary quantum number, and that tells you the energy level that we're in. And they're both in 2. So therefore it's that by e to the minus I, energy level 2, by time over h bar, which is the pixel. And this one is the same. It's that wave multiplied by that over time as well. And they're both 2, which means that the time component is using the same energy level, which means we can factor that out and put it here. You see? Now, if this wave function had a different energy level, so if this had 3 and that one had 1, then you couldn't factor it out, because that would be energy level 3, and that would be the ground state energy level 1. But they're both 2, right? So that means we can factor that out and have it here. So we've got these. Now, if you remember in the lectures, a couple of quantum mechanics lectures ago, we actually worked out roughly these type of things, right? And the way that I did them, if I can show it to you, is a very complicated method, which is, if I can find all of the papers. I don't think I have the papers, unfortunately. If there's only going to be 2 people, I might end this lecture early, actually. So I might not completely do it. Yeah, I might stop the lecture early. Okay, so we were able to compute these. So as I told you guys before, there are subwaves in dimensions smaller than our universe, which make up our universe's 2-dimension and a 3-dimensional quantum mechanical waves. Okay, so what we did here was we figured out what the radial wave function was, right? And I spoke about this in the last lecture, where I said that to make up a globe of a wave, you've got to combine the radial wave function and the angular wave function. Okay, so that was the radial wave function, and then that was the angular wave function here. Okay, so the individual 3D wave is made up of the radial function, which is the function of the radius, and then the angular function, which is the double angle, which made up the 3D object. And I gave a lecture on this, right? So those two, right, are made up of subwaves. And those waves, we can see them mathematically, but we can't see them in this universe, right? And those ones I showed you guys before. They're these ones here. If I can find, I just have to go back a couple of pages. Radial. There we go. Excuse me for a moment while I show you these wave functions. Somewhere, if they're here. Nope, they're not anywhere. Oh, that's not good, is it? That's embarrassing. I definitely have these wave functions. I know I've seen them. Where are they? Ah, further back. Ah, they're right here. All right, here they are. So the functions I just told you about, those, the radial and the angular functions that together make up the 3D wave, and then with time they make the 4D wave. Those waves are made up of like sub-dimensional waves that mathematically we can see, but we can't see them in the universe. It's quite fascinating. So here they are. These waves, okay? But these waves are actually made up of sub-waves. So just to explain it again, we've got the angular wave function and the radial wave function, and those together make up the 3D quantum particle wave. But the angular wave function and radial wave function are made up of sub-functions, which are waves that are like sub-dimensional, which I just showed you. But then those waves are made up of sub-dimensional waves of those, so sub-dimensional waves. It's pretty crazy, right? And here are the sub waves. These ones. So that's that one, that's P0, P1, P2, P3, okay? And what's interesting is that if you have something, for example, with a, it depends on the orbit of the electron around the nucleus, right? So if you have a atomic number that has a higher orbital number, then that requires a higher sub wave. So you build it up from the ground. So you end up using the sub wave, and then you build that into the sub wave. Then you get the sub wave, eat fresh, and then you build that up into the angular and the radial waves. And then you get those two waves and you combine them and you make the 3D quantum particle wave, which is an instant in time. Then you add the time, which is based upon the energy level, and you get the 4-dimensional wave. So that's how you build it up. And that took me about 2.5 hours the first time to do it. On a computer, it takes like 3 freaking seconds, right? Now that's for a hydrogen wave. For all of the other particles, almost all the other particles, there is no perfect mathematical way to solve to get the orbit, right? So mathematics to find them has not yet been invented. It is the waves themselves can only be sort of constructed, right? They have to be constructed what we call numerically, like trial and error. There's no actual mathematical equation for them yet, which is pretty crazy, right? So that's what's happening at the moment in the universe. So anyway, after the sub wave, then the sub wave, then the radial and angular waves, and then together they make the 3D quantum particle wave. Then you add time, you get the 4D wave. All right, so that's what we have right here. We're now up to where we were. Okay, so that's here. That's one of the 3D waves. That's another 3D wave because they have different orbits. And then combined, right, these two waves combined together with time, and that is the 4-dimensional quantum wave of hydrogen in this case. All right. Now the energy, the 3D energy is the pixel squared, slither of the pixel of the universe, times pi squared, the magic number, 3.14159, blah, 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 divided by 2 times mass times L squared. Okay. And this here multiplied by the energy level in 3 dimensions. Okay. Now, you don't need to know exactly what all these mean. So that's mass here, that's an orbit equation, right? But the whole point, right, is that when you put a 1 in there, okay, that becomes 1 and you're left with this. This, right, this is negative 13.6 electron volts, which is nothing, right? Like you'd need like, you know, millions and millions to heat up water, right? So that's a nothing. But each energy level goes up with the underneath squared. So what do I mean by that? I mean that if you want to go to energy level 2, right, it is 2 squared is just 4. So it's the first energy divided by 4. Okay, so that's the actual energy itself. All right. And so E2 is, that's the energy there for E2. Now, why is that important? It's important because it allows you, if I can find my working, to get the potential energy. Whoops. Hello. The energy allows you to find the potential energy of the particle, right, at its distance from the nucleus. Now, why is that important? And I'm going to go over this again. It's important because that allows you to find the atomic radius. It allows you to find the orbit, right, of the electron around the nucleus. So you know, for example, that, you know, let's say the Earth is a certain distance from the sun. You know that distance. And that's how we find the distance of the particle, the electron, from the nucleus. We know it because we calculate we construct the whole wave that I just showed you. And then from that, we use the energy level to find the potential energy. Once we have the potential energy, we can find A. And A is called the Bohr radius. The Bohr radius, right? Just Simon, hello, my friend. Bohr radius is the radius, right, specifically for us today in the hydrogen atom, of the electron in its relaxed state, okay, from the nucleus. Okay, so when you excite it, you will then know how far you need to find the electron away from the nucleus. Why is that important? It's important. It's absolutely important so that you can figure out when you excite a particle, which path is it going to take in a circuit board? How do you then figure out what particle is reaching you? If a wavelength comes to you, you know, what energy level is coming from that star, for quantum computing, for robotics, for mobile phones. It is so unbelievably important, right? So I will show you what I did, right, to actually figure out how to solve A. Now, if I can find it, let me just turn the page. Okay. So I took those equations. Hey. I took those 2 equations. Thank you, Captain Deltron. Just waiting for it to focus. Okay, these are the 2 equations. This is one sphere, snapshot in time. What's another 3D sphere, snapshot in time. Both have the same energy level 2. They both have the same type of orbital, which is 1, but they have the different magnetic orbital, right? So that's +1, that's -1 for the magnetic orbital, right? So I think that's the way that it's orientated. If it's upside down or not, I'm not completely sure on that because I'm in the mathematics of physics, not the actual, you know, the labels of physics itself. All right, so basically that's one equation, and where am I here? Yeah, sorry, I added them together and you get this, okay? Because it's these 2 equations. When you add them together, you get this, and I simplified it and I got this. And then you add the time to it, right? And the time was this energy wave here. And when you add time, you get this, right? So I'm not going to show you the actual mathematics of how I did it, right? Because we don't have that many people. But here, right, the actual wave, this is interesting. The reason it's interesting is because the wave itself is in an alternate dimension, right? You got the number I there. Now, that's quite interesting because it shows you that the wave itself exists across dimensions. Okay, and here, right, what I did was I solved to get V. Now, how do you do that? Well, when you want the V, see if I can find it. Here it is. Right, you want to find V. That's my room. Welcome to my room. Right, you take the wave that we just got. You get the conjugate, which is the mirror image of the wave in the other dimension. Okay, and you multiply it by the wave itself. So that by that, and in the middle, you've got the actual energy level. Right, and we know that's the energy level. And so when I put it together in the equation, then all I had to do was integrate it, right? And it's called the triple integral and multivariate calculus, which I'll teach you guys. I probably will start teaching you guys once I build up more guests. So here's my plan, right? I can live in a third world country or second world country on much less from Patreon. So at the moment, I'm getting like a couple of hundred, 180, 200 bucks a month on Patreon. Once we build that up, I'm going to probably go move to once I'm allowed to, a second world country, fingers crossed, my father's homeland. And then I can teach you guys online from there. And that way it will be much better. But up until then I can teach you guys calculus and do a lot more things, but I would love to do that. We'll see how we go. So anyway, here we have, right, the equation. Now I did all of the mathematics, right? And in the end, I was able to solve it and get this. Okay, now why is that important? Because all of these are just numbers except for A. All right, now I'll show you what the point is of that. Whoopsies, keep showing you my messy room, sorry about that. All right, so it's important because we've got here, what have I done here? Hold on, what have I done? I've missed something. Oh yeah, sorry. I missed one of my notes. It's one of my notes from yesterday. Alright, just Simon joined. So I'm going to go back over this again, right? But here you go. Alright. I'll wait for this to fix up. 3, 2, 1. There we go. Alright, so I ended up doing this integral, right? And I was able to figure out that because we know the rest state of the particle, and we know this is the second energy level. And the second energy level is, if you remember, the first energy level divided by 2 squared. So it was a quarter of the first. Are you a PhD? Yeah, good question. Soon I will be, yes. I've been offered to skip my master's and go straight into research. I was very honored with that. And it's called honors, and I was honored, which is this. Now, what's so cool about that? Well, we now know what the potential is of the energy in that state, which means that we can find A, right? Because A is the only unknown. So I'm going to come back and tell you guys again. Okay, so here is the energy, right? And so A is 0.529 by 10 to the minus 10 meters. So it is half of a tenth of a billionth of a meter. Half of a tenth of a billionth of a meter is the distance, is the radius of the electron particle in its orbit away from the nucleus in the second excited state for that spherical quantum wave function for hydrogen. So there you go. That's how people figure it out. All that work. So what did we do? I'll just quickly go. You would be an amazing teacher. Oh, thank you, Jen. That's very kind of you. Well, that's my plan. I'm going to build up Patreon as much as I can. Get The Tragedy of the Retarded Genius. Captain Deltron is awesome because he got a pre-ordered signed copy. But everyone else, you can also download the ebook for $5 at the letter X and then Libris, xlibris.com. Speaking Human, The Tragedy of the Retarded Genius. And I owe the upcoming book launch in very big part to Captain Deltron. Can we talk? Of course we can talk. You are a sweetheart, my dear. Absolute pleasure. And I look forward. There's also a book club. There's a fan-made book club. I'm not a part of it. They made it themselves on Facebook. I think it's called Speaking Human Book Club or something. It's pretty cool. I'm very honored with that. All right. So just quickly to summarize what we did, right? Conceptually. What we did was we went to the sub dimension of this universe. Life. And then we got that sub wave and we used it to build up the sub wave. Eat fresh. I keep saying that every time. And then from the sub wave, we then went and built the angular wave function and the radial wave function. And those two functions are the mathematics that actually create the sphere of the quantum 3D wave. Then we combined them and mixed it with time to get the 4D wave function. Once we got that full function, then we were able to find the potential energy. And once we found the potential energy, we were able to find the radius of the electron given that energy state in hydrogen away from the nucleus. And a computer can do all of that in 3 seconds, but it took me 2.5 hours to do all of the mathematics. And in the end, the whole thing I did together was like 8 or 9 pages of maths. Awesome source, yeah. So what I'm going to do, my plan is once we get enough book sales and Patreon and everything, I'm actually going to take you guys from the beginning to the end with calculus. And I have like a 1,000-page book, and it might take us a year, I don't know, or 2 years. We'll go through every single point. And if you follow every single thing and do every example, it would be very difficult for you to not become excellent in calculus by the end of it, or at least get it conceptually. That's it, guys. Gabversity, where facts don't care about your feelings. Simon, how do you want to chat, my friend? You, what do you want to do? You want to buzz me as soon as we're off this, or you want to tan? Oh, you want to talk? That's funny. Sure. Yeah, let's do it. Oh, it's always a pleasure, kind zone. I wouldn't do it if you guys weren't here. So it's always a pleasure. Did you ever see the 12-year-old autistic genius on TED Talks? I haven't yet. On Skype? Sure. I'll jump onto my Skype. Give me 10 minutes and I'll be on Skype and we'll talk. I haven't. I'll have a look at that, my dear friend. All right. All the best. Mwah. Facts don't care about our feelings.